Have you ever wondered why water remains water no matter how much you stir it or heat it slightly? What keeps the hydrogen and oxygen atoms together? The answer lies in a fascinating concept: chemical bonding. A chemical bond is the invisible force that holds two or more atoms together in a stable arrangement called a molecule. Without these bonds, the air we breathe, the food we eat, or even the cells in our body wouldn't exist. Atoms naturally tend to bond because bonded systems are more stable and have lower energy than free atoms. So, by bonding, atoms become energetically comfortable, like settling into a cozy chair after a long day. For example, in a water molecule written as H2O, that's one atom of hydrogen joined to one atom of oxygen. The atoms are bonded so strongly that the molecule stays intact through most physical changes. Now, to understand bonding better, let's first look inside the atom, the fundamental unit of chemistry. An atom consists of a central nucleus which contains two types of particles, protons and neutrons. Surrounding this nucleus are electrons, which move in fixed circular paths called shells or energy levels. A proton has a positive 1 charge and a mass of 1 atomic mass unit. A neutron has 0 charge, it is neutral, and also has a mass of 1 atomic mass unit. An electron carries a negative 1 charge and has negligible mass, it's nearly zero compared to protons and neutrons. These electrons are especially important in bonding as only the outermost electrons, called valence electrons, participate in forming bonds. So, imagine a small planetary system with a nucleus at the center and electrons orbiting around. This dynamic structure is what decides how one atom interacts with another. When atoms bond, they behave differently depending on whether they are metals or nonmetals. Metallic elements like sodium or magnesium usually have 1, 2, or 3 electrons in their outermost shell. These elements tend to lose electrons during bonding, becoming positively charged ions called cations. For example, sodium has one valence electron. It loses that electron and forms a sodium ion, written as Na with a positive 1 charge, or simply Na plus. Non-metallic elements like oxygen or chlorine usually have 5, 6, or 7 valence electrons. They tend to gain electrons to complete their outer shell, forming negatively charged ions called anions. Chlorine, for example, gains 1 electron and becomes chloride, written as Kil with a negative 1 charge, or Kil minus. This gain and loss of electrons is what leads to the formation of ionic bonds, where opposite charges attract and hold the atoms together. The number of valence electrons, that is, electrons in the outermost shell, determines how an atom will bond. Most atoms follow the octet rule, which means they try to have 8 electrons in their valence shell, just like noble gases. A few lighter elements like hydrogen and helium follow the duet rule, aiming for just 2 electrons. Let's take sodium, whose atomic number is 11. Its electron configuration is 2, 8, 1. That means 1 electron in the outer shell. It easily loses this electron to become stable, like neon. Now consider chlorine, with atomic number 17. Its electron configuration is 2, 8, 7. It needs just one more electron to complete its octet, so it gains that one electron to become like argon. When sodium gives up one electron and chlorine gains one electron, they form sodium chloride, common table salt, written as NaCl, which we say as sodium plus and chloride minus forming sodium chloride. When atoms interact to form molecules, we call this process chemical combination. There are two main ways atoms combine: ionic bonding, which involves the transfer of electrons from one atom to another, typically from a metal to a nonmetal. Example: sodium plus chlorine gives sodium chloride, spelled as Na plus Cl gives NaCl. Covalent bonding, which involves sharing of electrons between atoms, usually nonmetals. For example, Hydrogen gas plus oxygen gas gives water, written as 2H with a subscript 2 plus O with a subscript 2 gives two molecules of H2O. In both cases, the goal is the same: stability through a complete outer electron shell. And when a bond forms, energy is either absorbed or released depending on the type of interaction. That's why some reactions feel hot while others feel cold. The periodic table is more than a list, it's a blueprint for how atoms behave. Elements in group 1, like lithium and sodium, have just one electron in their valence shell. They easily lose that electron to become cations, positively charged. Elements in group 17, like fluorine and chlorine, have 7 electrons in their valence shell. They are highly reactive and readily gain one electron to complete their octet. So, lithium plus fluorine gives lithium fluoride, written as Li plus F gives LiF, an ionic compound. On the other hand, carbon, from group 14, shares electrons instead of transferring. So when carbon bonds with hydrogen, we get methane, written as CH4, with carbon in the center forming 4 shared covalent bonds with hydrogen atoms. This trend in electron configuration helps us predict whether a bond will be ionic or covalent, and even the shape and strength of the resulting molecule. Let's take a moment to wrap up everything we've learned. Atoms form chemical bonds to achieve stability. These bonds can be ionic, where electrons are transferred, or covalent, where electrons are shared. Protons, neutrons, and electrons form the foundation of the atom. But it's the valence electrons, the outermost ones, that determine chemical reactivity. We saw how metals lose electrons to form cations and nonmetals gain electrons to form anions. We also explored how the periodic table helps us predict bonding patterns using valence electron trends. Whether you're looking at common salt, carbon dioxide, or the oxygen you breathe, chemical bonding is what keeps the atoms together. In the next video, we discuss chemical bonding, diving deeper into the actual types of bonds like ionic, covalent, and coordinate bonds, and how they govern the structure and properties of substances all around us. See you there with more reactions, reasoning, and the real world magic of chemistry.